Okay, spanning tree algorithm, it is nothing but to solve the looping problem. The IEEE specification requires the switches uses spanning tree algorithm. Now, what is this spanning tree algorithm? If you observe the architecture, the block diagram given over here, we have assumed a system of connected LANs. Okay, I have assumed a system of connected LANs and its graph. Say there are 1, 2, 3, 4 LANs here. LAN 1, LAN 2, LAN 3, LAN 4, right? LAN 4, which has been connected. This is a system which has been connected to the switches. The names of the switches are say switch 1, switch 2, switch 3, switch 4, switch 5. Right, 5 switches are there and 4 LAN. In order to communicate from one point, from one LAN to the other LAN, we will be communicating through the switches. Say, for example, I want to transfer a data from LAN 1 to LAN 4. Okay, I want to transfer a data from LAN 1 to LAN 4. How it can take place? The frame can move from either in this path from LAN 1 to switch S1, next say LAN 2, next say LAN 3 and back to LAN 4, or from LAN 2 to switch 4 to LAN 4, or it can be in this direction from LAN 1 to switch 2, LAN 3, switch 5 in this direction. So there are different paths, right? Now, in the previous example, we have seen that in all the paths the frames will be transferred ultimately at the destination. Right now I told you around 3 paths are there, so 3 copies of the frames will be there, which will be of no use. So before transferring the frame, one need to find the shortest path from the LAN 1 to LAN 4. Okay, and once the path is found, the shortest path is found, and through that path, that is through a single path, remember it is not multiple path, through a single path the frame will be transferred. So the objective is to find the shortest path and a single path. So that solution will be given by spanning tree algorithm. Okay, a spanning tree is a graph in which there is no loop at all. Okay, it's a single path. This means that creating a topology in which each LAN can be reached from one another, from any other LAN through one path only. Okay, we can communicate from each LAN to the other LAN through only one path. Even though we have multiple connection, communication can be done through only one path. There will be no looping, so that we can avoid the multiple copies of the frame which is being transferred. So this is a general structure. Now using this, sorry, using the structure itself, we will go with the explanation. Next step is how to find the shortest path. Okay. Now coming to the graph representation. The previous diagram, I hope you are aware of the previous diagram. Just you need to make sure, just study this diagram. If anything is there, any sheet, any notes is there, just take down the diagram. This is important for me. Using this diagram, I'll be explaining next 2 or 3 slides. So just write it somewhere. Okay, or if you have PPT or something, just open it and keep. Fine. That is, say, I'll just explain the architecture again. 4 LANs, okay, which is connected to 5 different switches, right? Now for this, we are drawing the graph, that is graph representation. Okay, same thing. Say this one is LAN 1, LAN 2, LAN 3, LAN 4, which is connected to the switches. Same configuration, the previous one itself, continuation of the previous table. This is a graphical representation. Say S1, S2, S3, S4, S5. Okay, now for this, we are supposed to count, what is that? We are supposed to calculate the cost. Okay, cost of each say switch as well as the LAN. Say for example, if I consider switch, the data can be transferred from switch 1 to LAN 1. Okay, I'll consider this cost of transferring the data from this point to this point as say 1. The hop count, we call it as hop count. Okay, the hop count is normally 1 from a switch to the LAN. Okay, from a switch to the LAN, we will consider the hop count as 1. The reverse process, that is from a LAN to the switch, we will consider it as 0. Okay, so for all the configurations, you need to write down this hop count. Similarly, here you can observe from LAN to switch 2, hop count is 0. From switch 2 to LAN 1, hop count is 1. Similarly, for switch 2 to LAN 3, like that. Switch to LAN 1, LAN to switch, it is 0. So all this setup, you have to write the hop count now. This is the first step. Okay, is that clear? You can verify the other segments also. Say switch 4 to LAN 4. Switch 4 to LAN 4, hop count is 1. LAN 4 to switch 4, hop count, that is opposite direction, hop count is 0. Okay, now after this, After this, in spanning tree, now the next step is once you have written the hop count, we have the architecture, you have written the hop count, next is to find the shortest path and the spanning tree for a switch. Okay, you have to find the shortest path and the spanning tree. In the spanning tree system, remember spanning tree in the sense there will be only one path from any LAN to any other LAN. We need to make sure that is the main objective, right? To find the only one path from one LAN connection to the other LAN connection, and that path should be of the shortest distance. Okay, so these are the two main objectives for us. So in order to calculate the shortest path as well as the uh, shortest path as well as the spanning tree, the process has been described in this 4 steps. Okay, first step, the process of finding the spanning tree. First step, every switch, remember every switches, if you consider the previous diagram, just consider every switch. I have 5 switches in this example, which is named as switch 1, switch 2, switch 3, switch 4 and switch 5, and each switch will have its own built-in ID. Okay, each switch will be having its own built-in ID. Normally it is a serial number which is unique. Okay, and each switch broadcasts its ID. Whatever ID is given to that switch will be broadcasted, so that all switch will know which one has the smallest ID. So the first step is to, each switch has ID, that ID will be broadcasted, and the first step is to find the smallest out of, say in this example I have 5 IDs. Out of that 5 IDs, which is the smallest ID, we need to find out. So that is the first step in the algorithm. And the switch with the smallest ID, okay, which is selected as a root switch. Out of this 5 ID, the switch which has got the smallest ID, which is selected as a root switch, or we call it as a root of the tree. It say the bottom of a tree or root of a tree. Okay, from there, from that point onwards, it will be the reference point for me. From that point onwards, the distance will be calculated with respect to the other LANs or with respect to the other switches. So how to find the root switch? Root switch is nothing but IDs of each switches need to be considered. Out of each switch, you have to find the smallest ID. Okay, we assume right now in this example, what we will do is we will assume that switch 1 has got the smallest ID. Okay, switch 1, this one will has got the smallest ID, and this will act like a root switch now. Okay, so this is the first step. Once the root switch has been received, once we know the root switch, the second step, step number 2, that is the algorithm tries to find the shortest path from the root switch. Okay, it finds the shortest path, that is nothing but a path with the shortest cost from the root switch to other switches for the LAN. Okay, so how we are going to find the shortest path can be found by examining the total cost from the root switch to the destination. Sorry, that is the shortest path can be found by examining. Okay, right now what is my intention? I have a root switch now. From this root switch, I need to find the cost of each I need to find the shortest path through the cost. Shortest path in the sense path to be traversed from, say, switch 1 to LAN 1, from switch to LAN 2, whatever it is. Okay, so in the previous slide, we have seen that we have found the hop count, right? And we have assumed that hop count from switch to LAN is 1. Similarly, the reverse, LAN to switch is 0. Right? So based on that, we are going to find the cost, and accordingly, we are going to find the shortest path. Say, for example, from switch 1 to the LAN 1, the cost is what? The hop count is 1. So we will assume the cost as 1. Okay. Similarly, from LAN 1 to switch 2, okay, the hop count for LAN 1 to switch 2 is 0, right? So from here to here, initially the cost was 1. So 1 plus 0, we can assume it as 1 itself. So this cost will also be equal to 1. Next path, from switch 2 to LAN 3, right? Switch 2 to LAN 3, from switch to LAN, the hop count is 1. So 1 plus 1, the cost here is 1. So 1 plus 1, so this cost will be 2. So this is one of the path formula. Now, if I keep on increasing in this direction, the cost will start increasing, right? So I will terminate, I'll come back here. Now, suppose if you require a communication from switch 1 to LAN 2, so this is a direct connection, right? The cost of this from switch to LAN, the cost is 1. So therefore, it is 1. Okay. Now, suppose if you want to communicate from switch 1 to switch 3, so this will be the path, right? From here to here, the cost is 1. From LAN to switch, the cost is 0. So you can consider it as the cost, overall cost as 1 itself, right? Similarly, here from root switch to switch 4 if you want to calculate. So from switch to LAN, hop count is 1, therefore the cost is 1. From LAN to switch 4, the hop count is 0, therefore the cost will remain 1 itself. Now, if you want to communicate from switch 1 to LAN 4, if you want to connect it from switch 1 to LAN 4, either you can connect it from this point also, say switch 1, LAN 2, S3 or LAN 4, okay, or this path also, anyone will be selected, switch 1, LAN 2, S4 to LAN 2. So if this path, if I consider, if I calculate the cost from switch 1 to LAN 1, the cost is 1. LAN to switch is 0, therefore the cost of the previous, that is nothing but 1 plus 0, 1 itself. From switch to LAN, again the cost is 1, so 1 plus 1, it is nothing but 2. The cost will be 2 here. Now if you want to connect it to switch 5, either the connection can be done from this point to this point, that is LAN 4 to switch 5, or LAN 3 to switch 5, anyone again can be selected. If I assume this one, LAN 4 to switch 5, LAN 4 to switch 5, hop count is 0. Therefore, the cost is the previous cost of LAN 4, which is nothing but 2. Okay, so this is how we are going to find out the spanning tree. Okay, this is very important. This is very important with respect to the topic. You are going to find first the topology will be given. Accordingly, you are going to find the hop count, and after the hop count you're going to find the cost of each node, and you're going to find the shortest path, right? So you have done, you can observe here, you can come, if you consider the communication from one switch or from one LAN, say if you want to communicate from LAN 1 to LAN 4, okay, there is only one path, that is through LAN 1, switch 1, LAN 2, switch 4, LAN 4, right? Or if you want to communicate from LAN 1 to LAN 3, again there is only one path in this case. So this is how you're going to find out the cost. Based on the cost, you're going to find the shortest path. Okay, this is step number 2. Step number 1, identify the ID, smallest ID, and make it as a root switch. Step number 2, algorithm, and using the algorithm, find the shortest path. Okay, through that shortest path, you have to calculate the cost. Is that clear? The third one, combination of the shortest path creates the shortest tree. All this combination, this is nothing but it forms the spanning tree. Okay. Next, the fourth one, we mark the ports that are part of the spanning tree and the ports that are not the part of it as the blocking ports, with the block of which blocks the frames received by this. That is nothing but wherever there is a connection, okay, we call it as a non-blocking connection, and wherever there is no direct connection, that is nothing but ports are not connected. Say for example this one, S3 to LAN 3, there is no connection, so we represent it as a blocking ports. Similarly, S3 to LAN 4, there is no connection, so we represent it as blocking port. So this is the last final diagram of the earlier whichever architecture we had. You can observe here, continuation of the previous slide itself, S3 to LAN 3, there is no connection, so we represent it by a dotted line which indicates it is a blocking connection. Similarly, LAN 3 to S5, there is no connection, blocking connection. Similarly, S3 to LAN 4, there is a blocking connection. So this non-block is represented using this bold line where exactly the frames will be transferred. But we can, through this, we can make sure that there is only one path through which communication can be established. So figure shows the logical systems of the LAN with forwarding ports with the solid lines and the blocking ports with the broken lines. So port 2 as well as port 3 of bridge S3 are blocking ports. This one, port 2 and as well as port 3 of the bridge is the blocking. There is no frame is sent from of these ports. Similarly, port 1 of bridge S5, this one, port 1 of bridge S5 is also a blocking port, that is no frame is sent out of this port. So this is how it provides, the spanning tree provides a solution for the looping problem, where in the looping problem, we had multiple paths. Through that multiple paths, the frame is to transfer, because of which at the destination we had a multiple copies of the data, right? In order to avoid it, we went the spanning tree algorithm was introduced, where you find the shortest path, okay, for the frame transfer, as well as the cost you need to find, which will give you the spanning tree. That in general it gives you the one path for the transfer of frame one from one LAN to the other LAN. There will be only one path from one LAN to the other LAN, so that we can make sure that no multiple frames will be received at the destination. Okay, I hope it is clear. So coming to the last type of the connecting devices, router. Right, a router, it is nothing but a three-layer device. If you remember the block diagram, the first diagram which was shown in the PPT, first we started with the physical layer, which was hub. Next to it was a switch, a link layer switch, which is it falls on the two layers, that is physical layer as well as the data link layer. Next one is nothing but the router, which falls under all three layers, that is a physical layer, data link layer, as well as a network layer. So router is a three-layer device. It operates in physical, data link, as well as the network layer. Right? There are three major differences between a router and a repeater, that is nothing but a hub or a switch. The first one, a router has a physical as well as logical address, what we call IP address, for each of its interfaces. Okay, the router acts only on those packets. Okay, it will respond only on those packets in which the link layer destination addresses match the address of the interface at which the packet arrives. If there is a match with respect to the address, link layer destination address, then only those packets will be received by the network layer. And also the router changes the source and destination address, link layer address of the packet when it forwards it, and when it forwards the packet. That is nothing but it has to forward to other section of the internet. So in that case, it has to change the address, that is source as well as the destination address, and then it transfers. So basically at every network layers, at every network points, the physical as sorry the source as well as destination will be address will be changed, and then it will be transferred. Okay, so this is about the basic idea of the routing example you can observe here. So here we have a LAN connection. We call it as a one type a gigabit LAN. If the connection is within the LAN, then through the switches, the LAN communication can take place, right? This is nothing but we assume an organization, okay, which has two separate buildings. Okay, I'll consider this as one building, and this was other building, which has two separate buildings with a gigabyte internet LAN installed in each building. The organization uses switches in each LAN. Okay, within the building, if you want to communicate through the switch itself, you can communicate. Suppose if you want to communicate between the device from building 1 to building 2, then we have a switch over here, right? Two LANs can be connected to form a large LAN using 10 gigabyte LAN. Okay, again through the LAN itself, we are going to connect it so that LAN to LAN communication can be established. And along with that, the Ethernet technology that speeds up the connection to the Ethernet and the connection to the organization server. A router can, so here you can observe the switches again will be connected to the server, the organization server. If you want to communicate, if you want to connect these devices or the LANs to the internet, okay, other than the outside the organization server, then a router will come to place. A router is nothing but it can connect the whole system, okay, the entire system, entire organization, whatever it has been connected here to the LAN, it will be connected to the internet, to the rest of the internet. Okay, so if you want to communicate to the rest of the internet outside the organization, then the router will add its own source as well as destination address. Once it receives that through the data link layer, it receives the source as well as destination. It changes that source and destination based on the router's IP, and then it transfers the packet. Okay, so this is an example for the routing device. So these are the three main devices what we have in the communication. They're starting from the hub. Next is nothing but the switches, which is with respect to the data link layer, and the third one is router, which is with respect to the three layers also, network, data link, as well as the physical layer. Okay, this is about the three connecting devices. So the next topic, last topic under this particular chapter, it is nothing but virtual LANs. So what is this virtual? We have seen what is LAN in the previous slides, right? Oh, no, what is this virtual LAN? Station, if we consider, station is considered it's a part of a LAN, right? Station is nothing but it is a part of a LAN with, if it physically belongs to that LAN. If I consider a LAN, there will be different devices connected to that. We can physically are going to connect a particular device to that particular LAN. The criteria membership is geographic. What happens if you need a virtual connection between two stations belonging to two different physical LANs? Now, suppose say that when I say physical LAN, in one particular LAN, say various devices will be communicated, right? That will form one particular area. Okay, now suppose say that I want to communicate, I want to work with some other devices which has been connected to some other LAN. What has to be done? Either physically I have to rig up, connect through a wire through, that is nothing but through a switch. We need to communicate from one point to the other point. Physically it has to be done, right? So this virtual, instead of manually doing all that process, virtual LAN will give a solution to a certain extent. We can roughly define a virtual local area network. We call it as a VLAN, as a local area network configured by the software, not by the physical wiring. Here in this case, in the case of VLAN, physical wiring is not at all required. Through a software, through some configurations, you can communicate, you can have a connection from one LAN, from one particular station of a particular line to the other station of a other line. Okay. So how is that? We'll just go through it. So this is an example of a switch connecting three different lines. Okay, just assume this. Say we have a switch which has been connecting three different lines. In the first group, say I have three stations. Okay, because shows a LAN in an engineering firm in which 9 stations. Total here we have 9 stations, 4 plus 2, 6, 6 plus 10, 9. Right, 9 stations are grouped into three LANs. So here, say 3 in this first group, 2 in the second group, 3 in the third group. Suppose if this station wants to communicate with the station with the next one directly, the switches will do it, right? As well as if you want to communicate directly, you can do it over here. Now suppose here that this I'll assume as say one team. I will, if I consider some project or whatever it is, I can assume this as one team. Group 1 as one team, group 2 as other team, group 3 as other team. See, here we have 3 members, here we have 2 members, here we have 4 members. Now suppose say that I want to place the member within this, easily the communication can take place. And suppose if you want to communicate from this particular group to group 3, that also can be done fine. But now if there is a requirement like I want to change the team member, okay, suppose say that the member of group 1 I want to place it in group 3. So what can be done? How it can be done? Either what we have to do is either manually we need to unplug the connection over here and then place the connection to this particular LAN so that it forms a team over, right? It has to be done manually. Physically it has to be done. So here, what would happen if the administrators need to move the engineers or the team members from their groups? So in that case, the LAN configuration need to be changed, right? The network technician must rewire the entire configuration. So in a Swiss LAN, changes in the work group mean physical changes in the network configuration, right? So in order to avoid these physical changes, this virtual LAN was introduced. So this is the basic architecture of virtual LAN. This is a switching using virtual LAN software. You can observe here. Okay, the whole idea of virtual LAN technology is to divide a LAN. This is a single LAN, so okay, saying into logical segments instead of the physical segments. Okay, you can observe here the first section we have divided it to VLAN 1. This is a logical division, VLAN 2 and VLAN 3. In VLAN 1, which are the devices placed? Okay, through software we can achieve it. In VLAN 2, which are the devices placed? In VLAN 3, which are the devices placed? So LAN can be divided into several logical LANs called VLANs. Each VLAN is nothing but a group in the organization, right? Each VLAN is nothing but a group in the organization. Any stations can be logically moved to any other VLAN. So through the software, if I want to place this particular station to VLAN 3, through software I can easily do that. A reconfiguration or rewiring is not at all required, right? All members belonging to the VLAN can receive broadcast messages sent to that particular VLAN. If a station moves from VLAN 1 to VLAN 2, it only receives the broadcast messages sent to VLAN 2 and there is no need to change the physical configuration. So through software directly I can change the whichever stations are there in a particular LAN. I can remove a particular station and place it in the other VLAN, other virtual LAN, right? So this is the configuration of VLAN. So in VLAN also you can have or different categories like grouping also can be done in VLAN also. You can observe here 2 switches in a backbone using VLAN software. This is a backbone switch. The backbone switch can be connected to different switches. In this case, 2 switches are being given, so switch A and switch B, right? Switch A has been under switch A, various stations will be there which will be connected to a particular LAN, particular area of a LAN, that is virtual LAN. Similarly, switch B also. Here also you can observe switch B, if you want to communicate, switch B particular station as well as switch A particular station can be placed in a particular virtual LAN. Okay, that is nothing but it means that virtual LAN technology allows the grouping of the stations connected to different switches in a LAN. So grouping here in the grouping can be done with respect to different stations which has been placed in different LANs. It can be grouped together through the virtual LAN. Okay, so this is about the virtual LAN software.